According to the modern cosmological model, the most influential being the Big Bang Theory, our universe originated from a singularity 13.8 billion years ago. It is still in a state of accelerated expansion, faster than the speed of light. Because light takes time to travel, this superluminal expansion of the universe limits our view. Light from some distant regions will never reach Earth, and we will never be able to observe their existence. Therefore, no matter how advanced our instruments are, we can only observe the universe within a radius of 13.8 billion light-years from us. Taking into account the continuous expansion of the universe, scientists have adjusted the limit of this observable universe to 46.5 billion light-years. This is a spherical space with Earth at its center and a radius of 46.5 billion light-years. The surface of this sphere is called the cosmic horizon. Beyond our cosmic horizon, there could be an infinite number of spaces just like ours, with a radius of 46.5 billion light-years. These are parallel universes that share the same physical laws as ours. According to Einstein's theory of relativity, the speed of any object with mass and the transmission of information cannot exceed the speed of light. This means that, under the universal speed limit of light, we can not only never observe the parallel universes beyond our cosmic horizon, but we can also never exert any influence on them. In other words, the parallel universes outside our world are completely independent of us. Because the number of particles in each parallel universe is finite, if we set an upper limit on the precision of our observations, the number of possible arrangements of all particles would also be finite. Therefore, in an infinite number of universes, there must be universes identical to ours, and there must also be an identical you, and a second you, a third you, a fourth you, and an infinite number of U's. These infinite U's are separated by infinite scales of space and can never have any relationship in the physical world, which is why they are called parallel universes. Another type of parallel universe is derived from inflationary theory. In 1964, Penzias and Wilson of Bell Labs in the United States accidentally made one of the greatest discoveries of the 20th century while testing the antenna of the most advanced radio telescope at the time, the cosmic microwave background radiation. Two previously unknown young men suddenly became famous overnight and won the 1978 Nobel Prize in Physics. So why is the microwave background radiation so important? Because according to Gamow, the father of the Big Bang Theory, if the universe really did experience a Big Bang, then a type of electromagnetic radiation that fills the entire universe must remain. And theoretically, this electromagnetic radiation can be detected. Thus, the discovery of the microwave background became the strongest evidence supporting the Big Bang Theory. On March 21, 2013, the European Space Agency released a panoramic map of the cosmic microwave background radiation from the Planck probe. People discovered that the universe is highly isotropic on a large scale. This indicates that there must have been mutual connections between distant regions in different directions of the universe. However, in the standard Big Bang model, the matter after the birth of the universe was thrown to distant places before it had time to establish thermal equilibrium, leaving insufficient time for a causal connection to be established between the two space-time regions. This contradiction is called the horizon problem. To solve this contradiction, physicist Alan Guth proposed the inflationary theory in 1980. This theory states that in a very short time after the Big Bang, between 10 superscript 3 and 10 superscript 3 superscript 3 seconds, the universe underwent a period of exponential expansion. In this fraction of a second, the scale of the universe suddenly increased by a factor of 10 superscript 2, which is like a speck of dust instantly expanding to the size of 10 Milky Way galaxies. This process allowed regions that had already established thermal equilibrium to maintain the same temperature after losing causal contact. The energy for inflation comes from the inflaton field, which can generate a repulsive force, causing the scale factor to grow exponentially. And as space in the universe expands, the inflaton field will generate even greater repulsive forces, so the inflation of the entire universe has never stopped and will never stop. Due to some quantum mechanism, anomalies will randomly appear in certain regions, like countless small bubbles suddenly appearing in space. Within these bubbles, the energy of the inflaton field is converted into particles. The particles form matter, and the matter forms galaxies, stars, planets, and even evolves life. We live in one of these bubble universes. Between us and other bubble universes is a cosmic space that is in a state of perpetual inflation. Almost every second, countless new universes are randomly created. They are independent of each other, but they may also collide and be destroyed or form new bubble universes. In their study of the cosmic microwave background radiation, scientists have already found 4 patterns suspected to be formed by the collision or friction between bubble universes. Because the initial conditions of these bubble universes are different, their physical laws and even spatial dimensions will be completely different. For example, in other universes, there may be no gravity, the speed of light may be slow, or there may be different elements, and so on. The third theory of parallel universes originates from the many-worlds interpretation of quantum mechanics. Quantum mechanics has 2 famous classic experiments, Schrödinger's cat and the double-slit experiment. Both experiments involve the wave function collapse problem in quantum mechanics. Simply put, wave function collapse means that in the quantum world, the state of a microscopic substance is random and uncertain when it is not being measured. For example, Schrödinger's cat is a thought experiment about quantum theory proposed by Austrian physicist Erwin Schrödinger. A cat is placed in a sealed box. A radioactive atom in the box has a 50% chance of decaying and releasing poison gas that kills the cat, and a 50% chance of not decaying, in which case the cat survives. According to classical physics, one of 2 outcomes must occur. The cat is either dead or alive. However, according to the Copenhagen interpretation of quantum mechanics, because the decay of the atom is uncertain, the cat is in a superposition of being both dead and alive before the box is opened. Only at the moment of observation, when the box is opened, does it collapse into a definite state. However, besides the Copenhagen interpretation, there is another quantum mechanical theory called the many-worlds interpretation. This theory suggests that the so-called wave function collapse is actually the universe splitting. When the box is opened, 2 parallel universes split off. We are just randomly assigned to one of the universes with either a dead cat or a live cat. If this theory is correct, it means that every choice you make in your life splits the universe and creates 2 yous. For example, at a crossroads, the you who chooses to go left and the you who chooses to go right will enter different parallel universes. Your life is constantly making choices, and the universe is constantly splitting. And your destiny will have countless development trends. The countless yous in countless parallel universes could be a chef, a teacher, or a billionaire. Infinite yous experience countless different lives. But for you, once you have made a choice, it means giving up another possibility, and you can never change it. Therefore, under the theory of quantum parallel universes, there is no master-slave paradox. Even if you could travel back in time to change history, you would only be changing the life of another you in a parallel world.